All right, everybody, welcome to the TST meeting. Today we're going to talk about basically the state of our distributed system and some discussion about some of the proposals for a number of enhancements. And Jordan is going to lead the discussion. And with that, I'm just going to pass it to Jordan.
Yeah, so in the wiki for this meeting, I put this document that I wrote that I've been working on for since I started here, pretty much just taking notes on issues that I found with the distributed system, sort of deficiencies in architecture and things like that. I don't really expect people to read that because it's tons of stuff, so I put together some slides of the most interesting things that I'm looking at short term, and I'll just go through those. And so basically, I'm just going to talk about, yeah, like I said, just potential improvements to the distributed core that I see. So yeah, the motivation is provide an overview of the state of distributed systems in ONOS, offer suggestions of how they can be improved, and solicit feedback on how these things should be prioritized, what should be thrown out, what we should be focusing on, things like that, what people are interested in. So just sort of, I'm not going to go through an architecture of distributed systems in ONOS. This is just one page, but so sort of the different layers of distributed systems that I see are messaging, cluster management, Copycat, which is the RAF implementation that I wrote, Atomics, which Atomics essentially manages our primitive state within the RAF implementation, allows you to create primitives and delete primitives and things like that. On top of Atomics, we do partitioning, and then obviously on top of all that stuff, we have a bunch of primitives that are sort of separated into two categories: strongly consistent primitives, which use the consensus protocol, and eventually consistent primitives.
You mean by cluster management?
So that includes like the failure detection protocol and just tracking the nodes that are in the cluster. I mean, so there's like a cluster manager class that essentially exposes what nodes exist.
Detecting when nodes are becoming slow or unresponsive, right, or if they're dead, or if it's network partition,
yeah,
or if things are being rebooted, or
right. Yeah, and that's pretty. I mean, the top two, the lowest layers, are pretty solid. I mean, Netty is an awesome framework. The messaging seems pretty solid on it. Cluster manager. So what I'm going to talk about is everything that's on top of that, basically. So first, Copycat. So sort of what I found over the last couple of months of debugging various HA issues, just spending tons of time inside of debug logs and things like that, I realized that sort of there's a fundamental design flaw in Copycat, at least as it pertains to the concept of primitives and partitioning on top of it. So the problem is that Copycat really treats everything that interacts with it as a single application. So whether you create one primitive or 1,000 primitives, it manages consistency for all of them as if it's a single object. And so that's extremely limiting in terms of performance. Essentially, I mean, the whole concept of consensus is that it ensures that everything happens in order and in real time. And so it's enforcing order across 1,000 primitives if you create 1,000 primitives, which isn't useful, especially when you consider that ONOS has a bunch of different applications running. All of them can be using different primitives that are totally independent of each other. And so it doesn't even make sense to be managing consistency across all those primitives. And so
what do you mean by primitives?
That's like the maps. So we have higher level APIs that are similar to Java data structures, but are distributed versions of them, like maps, sets, redirectors. So those are all the primitives. So anything that you can build with the storage services, basically a primitive. They implement this base primitive interface. And yeah, what I noticed is, well, also there's another aspect to the fact that these are all sort of managed as a single piece of state. I noticed during a lot of debugging, a lot of what we see are timeouts due to, like, if there will be a bug inside the protocol that causes a timeout on clients. And often what I'll see is one timeout leads to 100 other timeouts. And that's and in any area of the system, like there's a timeout in a map that causes, and then after that a timeout in a leader elector, and after that a timeout somewhere else, in like totally different applications. And so sort of re-architecting how individual primitives interact with the consensus protocol can encapsulate those things from each other so that they fail independently of each other, but also their consistency guarantees are achieved independently of each other, which will get a lot better performance. And so that's what this is about. And so some of the things that I proposed for doing this inside that document are rewriting logs. So sort of from the start of Copycat, what we did to try to, I mean, the most important thing obviously is correctness. And so we simplified the internals of the server. I mean, there's several threads, but the threads are really limited to make it simpler to reason about what's going on so we can get the protocol correct. But now that the internal protocol inside the servers is pretty solid now. And so what needs to happen to sort of support better concurrency is rewriting logs so that I can support like read-write locks, replicating to followers and parallels. There's a lot of parallelism that could be taken advantage of inside of Copycat servers that's not currently taken advantage of. And then on the client side, for the issue of primitives all being represented as a single piece of state, to sort of solve that problem, I proposed sort of rewriting the client so that it can manage essentially each primitive can have a logical client that does its sequencing. So inside the client, it does sequencing for ordering guarantees. And that's where a lot of the time you'll see failures across primitives because one primitive is like waiting for an event that it knows it's supposed to come, and it's blocking all the other primitives from receiving events. And so sort of what I proposed is rewriting the client so that it treats each primitive as having a separate session that has separate guarantees and orders things separately, independently of all of this. And then similarly, taking advantage of the same sort of parallelism inside of state machines. Essentially, each consistent primitive is represented inside the RAF protocol with a state machine, and the state machines never interact with each other, so they should be also be done, like operations should be applied to them in separate threads.
So just a point of clarification though, I mean, all of these enhancements effectively are just inside the box, but they don't change the API, right?
Right. Yeah.
So that's a nice thing, in a sense that a lot of this work can be done without any impact down, other than in terms of performance, but down the line. So that's actually that's great. Just to me, actually, says the architecture is right. Perhaps some of the individual design choices maybe were not optimized for this part of the use case, but I think the architecture is great. If that's the case.
Oh yeah, I think it would be. I think this would be a huge improvement over what we currently have in terms of encapsulating primitives from each other and just seeing better performance.
Are you proposing there will be a separate instance of the RAF protocol for every primitive, or you're...
No, it's separate sessions. So inside of RAF, essentially consistency guarantees are provided within the context of a session. And the problem is we can't just create a separate client for all the primitives because sessions have overhead. They periodically submit keep alives, and the interval at which keep alives are submitted impacts failure detection. So we can't just create a ton of clients and set their keep alive interval to 10 minutes or something like that. So anyways, yeah, so it's still a single, we have separation between RAF protocols, instances of the RAF protocol, those are partitions. So this is sort of separate, splitting that up further, splitting sessions up instead. So we split the RAF protocol into partitions, and this is splitting sessions into logical sessions, I guess. Any other questions?
And this is great. So is there, but you have more, right?
Yeah.
So I'll let you keep going.
So sorry to interrupt. I don't know how to do this without sounding harsher than I really mean, I'm sure. So given we're looking at this kind of re-architecture, and I understand it's an internal re-architecture, not changing the API, does it make sense at this point then to also say, how would we re-architect this if we were to say, rather than have ONOS storage included in kind of the core process of ONOS, allow that storage to be external to the core process of ONOS as well as persistence, using maybe an off-the-shelf tool? And how would that work into this architecture at the same time?
So David, can I take that discussion offline with you? Definitely need to address
Absolutely.
that. I think it'll be done
Absolutely.
in the proper context. I think there is still benefits of doing this this effort, but I think there's definitely some broader picture we need to consider. But I would prefer if you don't get dragged into it in this session. Is that
okay?
Fair?
Yeah, I just didn't know if there was some relevance here that around that, but yeah, we can take it offline, no problem.
Yes. Great.
All right. So yeah, and then so that was copycat. That was sort of the big architectural flaw I saw in copycat as far as how we're using it. So as I said in the intro, Atomics is what sort of runs on top of copycat, and it's what it's how we use it to actually run each partition of the cluster. And so the thing I noticed about Atomics is it does support sort of evolving clusters insofar as you can add nodes to it and remove nodes to it, but there's sort of some limitations to how it performs in those types of circumstances. And so I'll explain what that means. So one of the things is like nodes, when you add a node to an Atomics cluster, it can block the cluster. And this is actually a pretty simple thing to fix. But the problem is, like, hypothetically, if you have a one node cluster and add a second node to it, you're increasing the quorum size from 1 to 2 because consensus requires the majority of the cluster to be running. And so the cluster will be blocked until the new node comes online. So the fix for that is not adding the new, or catching up the new node before it's added to the cluster. The other interesting thing that I noticed a lot in ONOS is hotspotting. So a lot of the times, just based on how the order of how you bring up the nodes in the cluster, the RAF protocol will elect the same leader for several partitions. You bring up a 3-node cluster, 2 nodes are required to reach consensus. The second node gets elected for 3 partitions. And so what that means is you have basically all the rights going to that node, all the replication coming from that node, and so just a lot more overhead on that node. And
why does this change it instead of electing load node 1, you elect node 2?
you're just spreading
I mean, if I understand you correctly, you're saying whatever node is the leader of the cluster has a higher load.
Yep.
So why does it matter if we just use the same node?
So there's leader with respect to different topics. There's not a leader. There is not the leader. There is a leader for particular subject.
Yeah. So in a 3-node cluster, there's 3 leaders. The optimal setup is for each node to have 1 leader.
Oh, I see. Okay, so you're saying there's more than 1 leader based on different, for different.
Yeah.
What did you say?
Topics.
Partition. Yeah, by default, there's
Yeah, you're right.
by default there's essentially one partition per node in an ONOS cluster. So a 3-node cluster has 3 partitions. That means 3 leaders. Often, what I see is they'll all get, or at least two or three of them will be on the same node. And obviously, the optimal way is to spread them out. And I think this is only something that I've observed. I don't have proof for it. But I would expect that this results in a lot more consistent performance anyways, over the lifetime of a cluster, because a node, and then like later on in a cluster, in the lifetime of a cluster, a node crashes, there's leader changes. When that node comes up, ideally, a leader could be reassigned to it. And so, yeah, that's pretty simple. And then the last thing about sort of cluster, just how clusters operate is, the other thing about partitioning is, say, like by default in a 7-node ONOS cluster, you have 7 partitions of 3 nodes each. The problem is, so normally in consensus, you can tolerate the failure of a minority of nodes. So in a 7-node cluster, you could tolerate the failure of 3 nodes. But if we have a 7-node ONOS cluster with 7 3-node partitions, the failure of 2 nodes.
Chances are it's going to take number of partitions offline.
Yeah, the failure of 2 nodes can result in loss of availability of a partition, and that can mean a lot of writes to a map fail, or even a lot of operations can't be done at all, like a map size operation or clear or transaction, things like that. And so one of the things that I've experimented with in the past is sort of proactively replacing nodes that crash. So obviously, even though a partition takes up 3 nodes in a 7-node cluster, we still have a bunch of other nodes that could potentially replace a failed node. And so what I've experimented with in the past was doing that. A node, the consensus protocol detects that a node can't be reached, and it just catches up another node, a backup node, and adds it to the partition so that it increases the failure, or the number of nodes that can fail back to 1.
So the only caveat would be if you have actually a network partition or simultaneous failure.
Yeah, two nodes. Yeah.
What you're saying is that actually, even if you have a 7-node cluster, failure of 2 of those nodes could actually take out parts of the cluster, right?
Yes.
Even though you would think that with a 7-node cluster you could survive 3 failures.
Well, that doesn't make sense. Like, why would you want that?
Well, you don't want that. So if I can jump in, feel free to permit. The reason for keeping the number of nodes in a partition small is to minimize the chatter and to increase the speed of achieving consensus, right? Because if you were to, let's say, have a 13-node cluster with everybody's member of every committee, then it's going to be difficult to keep everybody up. The performance is going to tank. So for that reason, you want to keep the size of each sort of consistency group or partition as small as possible. But when you do that and you sort of spread the responsibility evenly through the cluster, chances are that if you take 2, and we assume, let's say 3 is the size of each partition, then chances are that failure of 2 random nodes is going to result in some number of partitions being affected in a way where they can't keep going. And you have availability issues for the partition, and and as a matter of fact, your system as a whole is.
Yeah.
So
I guess what I'm puzzled about is like, sure, you have some. It looks like your partition size is sort of your minimum consistency sort of size, and so everybody has to be up to date. But I mean, I think what you're saying makes a lot of sense. There's just there are a lot of other people who are going to be up to date at any given time when you have a failure. So certainly, although your actual partition size may be smaller, your sort of virtual or practical partition size is actually bigger.
yeah, so I think this is a good point. The only caveat to it is if 2 nodes fail at the same time, you can still suffer availability issues. But I think that's it's a narrower set of failure cases.
I mean, I guess the interesting thing is that if two nodes fail at the same time, you may only have one other node in the partition, but you may have all these other nodes, like you say, that are up to date and can actually be used, right?
Not in that case, because the problem is that you have to have a majority of nodes to do a configuration change. To add a node to the partition, you have to have a majority of nodes. Otherwise, rights can be lost and consensus.
Okay, I guess I didn't understand it well.
You can also change the default partition size.
Right.
If you want to tolerate more than one.
So another strategy would be to achieve sort of a balance between cluster size and minimum partition size. Generally, the idea would be that if you opt for a larger cluster size, like 7 or higher, that probably means you not only want to achieve higher scalability, but probably also you're likely to want to achieve higher availability. And so that maybe a partition size of 5 would be better choice. In that case, you can still tolerate failure of 2 nodes.
Yeah, I mean, basically the other question is, how much worse is it to have a partition size of 3 rather than 4? It would seem like it should be drastically worse, but maybe it is, I don't know.
Yeah, we have an experiment.
That might be interesting to know. I mean, that goes, it's precisely follow up on the thing, basically, like, maybe it's something you kind of want to try to optimize, like figure out, well, what's the best size that balances performance. And maybe, maybe there's no cost for adding up, for making the partition one bigger, or maybe it's a horrible cost for making it one bigger and you really don't want to do it.
But I think, so some of those things can be done today just through recommendation and configuration, right? Basically saying, if you're going with 5, you might want to choose, if you're going with 7 nodes, you may wish to go with let's say, a partition size of 5 nodes. Just a recommendation. And you can do that today without any coaching. Anyway,
it's hard to make that decision now if you don't know how it's going to affect the performance.
All right, so so that's my sort of atomic spiel. I guess not. So last thing I sort of noticed just working in the code for the last few months is I think the lines between Atomics' responsibilities and ONOS' distributed core are really blurred. Sort of the things that ONOS users interact with, the primitives that ONOS users interact with are currently a mixture of Atomics primitives and ONOS primitives and Atomics clients and ONOS clients and state machines from both projects and things. And so obviously that bothers me, and I'm interested in combining at least some of the code from ONOS with Atomics. And sort of the rationale for this is obviously a lot of this stuff is really cool and really useful in general for distributed systems, and it's currently hidden inside of ONOS.
Yeah, this is something we've been talking about for a while, which is that it's logically independent of ONOS, right? So it doesn't necessarily, it logically probably should be separate from it.
Yeah.
So the proposal here is basically to take some of those primitives, sort of put them into Atomics.
Really take all of the primitives out of ONOS, all the ones that aren't ONOS specific. And
fine.
I think that is ONOS specific should just be like a subclass or a specialization or.
It's the source. The stores are ONOS specific, but the primitives themselves are really not.
Yeah, that's where actually the separation stores.
Even the stores are possibly, something that maybe should be its own module and just, the schema obviously is going to be ONOS specific, but the mechanism, and implementation seems like it would be very generic. It should be in both cases, for the stores and for the.
Yeah, I completely agree.
Well, anyone else? All right, so the sort of way that I see that I think I can go about doing that is right now. So if we were to take on the copycat refactoring, that sort of eliminates a lot of what Atomics is doing for the ONOS primitives, which is managing state machines. Because what I'm talking about in copycat is increasing parallelism and sort of allowing multiple clients to interact with multiple state machines, which is a lot of what Atomics does right now. And so the way I think we could go about separating out the ONOS primitives into atomics is essentially by merging atomics back into ONOS, which is the resource manager, the client, and the primitives that are still in atomics that are used inside of ONOS back into ONOS, getting everything working, cleaning it up there, and then I think it's pretty simple from there to move that stuff back out. And that's my thoughts on that.
Yeah, what's the rationale for this, process of like, merging it into ONOS and then moving it back out?
Just because a lot more code is in ONOS than in atomics, and because it's easier, I feel like it's easier, yeah. There's less code in atomics to move into ONOS than there would be to move from ONOS back into atomics. But, and also I guess I sort of feel like that makes me more comfortable that it will still work correctly. I don't know. I feel like there's refactoring that has to go on if we move from code from ONOS into atomics, because there's different module structures and things like that, and that refactoring sort of increases the overhead of moving in the other direction.
I guess you don't have to release versions of atomics to sort of synchronize there. Yeah. I think you should pick whatever approach makes it easier.
Oh yeah, I agree.
I think we can, because I think
I'm
we can.
sort of interested in why you chose this. This is interesting.
But I mean, some of the risks here would be that we inadvertently bake in some dependency on ONOS, but I think we can mitigate those risks very well.
Yeah, I mean, and certainly from an ONOS perspective, that doesn't mean bad, right? I mean, it's not going to perturb ONOS and merge stuff into it. It's running as usual.
And we plan to disaggregate it, and then we just this would then get disaggregated.
Yeah,
back out to
it becomes a separate thing.
Yeah,
The ONOS distributed,
the idea,
which is AKA atomic 2.0.
but the idea would be you would move it into the existing atomic repository, right? Yeah.
And it would become version 2.0.
Exactly. That's great.
Yeah, that would be great.
So yeah,
I mean, assuming, well, I don't know the structure of the atomics project, or just the boss of atomics, that you can do whatever you want. But presumably other clients of atomics wouldn't be distressed by this.
No. That'd be great.
They're just suddenly.
I mean, my thought is that, well, I would love it, right? Wait, I get all these primitives, cool, right?
Yeah, there's so much
awesome.
awesome.
Good, right?
There's so much awesome stuff. And then, so yeah, the last thing, I think it's the last thing. Yeah, last thing. The last thing I sort of chose from that document is, I've been hearing this a lot, where there's a need sort of for people want to use consistent map, but it's too slow, there's not enough performance, they want something like eventually consistent map that's not eventually consistent.
Yeah, I think those people are idiots and should really just use eventual consistency and learn to live with it. But,
right, yeah.
I mean, probably most distributed system people would tell you that too.
Yeah, that's true. Yeah, it's all about trade-offs. But yeah, but there are some other protocols that we can do. So there's sort of like an in-between. There's a protocol that's sort of in between gossip and consensus, which is consistent hashing. And so what I'm sort of proposing is an in-between where it should perform just about as good as an eventually consistent map, but they call it eventual strong consistency. Some people call it that, where this sort of data structure guaranteed strong consistency, absent network partitioning, basically. And yeah, it would be an in-memory, basically an in-memory data structure. Essentially, it's hashing keys to nodes and replicas, hashing keys to nodes and backups. And yeah, that's all I
How
got.
does that perform during network partition?
Lose data, right?
You can lose data, yeah. Depends.
But in terms of, so what's your take on, so I guess, before I ask my question, my viewpoint on the consistent hash would be that would be the last priority.
Oh yeah, no, definitely.
But then between the improvements to copycat and then sort of refactoring atomics to incorporate a lot of the, sort of promote a lot of the ONOS primitives into atomic. Where those two other activities fall, in your opinion, in terms of not necessarily priority, but in terms of what would make it easier for you to, or for this work to get accomplished? Is there any relation between them, or?
I don't think there's really a relation between them because whether copycats being used inside of ONOS or copycats being used inside of atomic for the same purpose doesn't matter. But I definitely favor and have started working on some of this copycat stuff just because it seems like such a huge benefit. And yeah, I'm not really in a hurry to sort of move code back out of ONOS or move atomics into ONOS. My priority is more doing it at the right time when it makes sense.
So it seems like then in that case, it seems to me the copycat stuff should probably have to be first then, in terms of priority than the atomic. Yeah, and then there's this stuff. This is stuff that I've just known about for a long time and haven't prioritized because nobody's complained about this type of thing. I mean, the copycat client things those affect bugs that I've been looking at for the last couple of months. Sure, but for the hotspotting, for example, right? For hotspotting, there could be, for some of these mixed bag of issues, there could be individual sort of potentially transient solutions, right? For hotspotting, you could create a command to rebalance, force rebalancing things, right? Or have some sort of a deliberate steps for when we do that after, discrete steps, right? I mean, that might solve that problem.
Yeah, it seems like that's pretty easy to do.
Regarding people not complaining, I think, a lot of the times people when they complain directly about it, right? It's like, the problem is like, well, I found a pod that, my batting average starting opponents is probably good for baseball, but not good for a network operating system, right? That often it's really slow to start up, and I observe timeouts, and I also observe excessive like resource usage, it's using up too much, pegs my CPU or various things like that. So I think people observe the side effects, but it's really not obvious what the root cause is, right?
Right, yeah.
Like I haven't done a careful time to event analysis of what's causing, why does it take 3 minutes to start up ONOS? It seems, I complain about it and file bugs on it, but I don't know what the root cause is.
So on this page right here, it seems like a lot of these things can be temporarily taken care of through documentation or some substitute.
Yeah, I guess all three of them can.
For me, the big ones are increasing the parallelism and copycat. Boost up the performance, and then the primitives. And I'm actually really interested in having the primitives promoted up to atomic. They're sort of good for us for a number of reasons, right? It sort of reduces the overall liability. I mean, we're still liable for the code, but now it's useful by and have more eyeballs on it from other people. And technically doesn't necessarily directly count against sort of debt of ONOS, right? The liability of the code side.
Yeah, there are lots of advantages. Plus, I think in some sense it could be sort of one of ON.Lab sort of kind of high impact contributions in some sense.
Exactly.
Exactly. Not even not just in network operating systems, but in launches.
Oh yeah, tubes and tons of different projects, databases in general.
Yeah, I want to put in a plug for anything that improves the startup time and reduces kind of busy waiting that burns your CPU, because that's something that I believe affects. You may not think it affects us, but it affects all of us. Like every ONOS developer, because every time you restart ONOS, it's slow, and every time you restart distributed ONOS, it's particularly slow. And so anything, when I look at things like, reducing hotspotting, that sounds like a really good idea. Reducing timeouts, that also seems like a really good idea. And because it's multiplicative across everybody who's we restarted 10 times a day, right? And every time we restart it, we have to wait.
Sure, but so I'm completely agreement, but just to set your expectations, I don't think any of these things would necessarily impact the startup time. And also as a side note, I mean, that's one of the reasons.
I think the multi-threading could drastically improve startup time because you're not blocking. And like you said, cascading timeouts are exactly what I see on a startup, right? Yeah. And the things, and also when it does
so much cascading timeout exceptions, right? So when one occurs, others occur. And so you're seeing slowness even when no exceptions occur. So, I mean, it clearly it couldn't hurt, but I'm just be careful where you set your expectations.
Well, I'm not sure. Well, it may not help, but my thought is that, if you have the situation where, messing with one object blocks all these other objects that people are waiting on, that sounds like something that could, that you're serializing what could be parallelized, right? And so your startup's not going to be good in that case.
No, that seems like such a huge thing to me.
But we'll see, I guess. But anyway, my hopes are, every time I the things I'm seeing are timeouts and sluggishness, and that tends to, usually when you have stuff like that, is because somebody's waiting on some other resource or somebody's waiting for some reply, and somebody's waiting because they need something that they can't get. And,
sure, but also keep in mind that ONOS was designed to, a lot of the pieces of ONOS are designed as effectively kernel extensions, right? So rather than restarting the entire kernel, i.e. rebooting ONOS or a cluster, you are free to actually just load individual modules, unload them, load them, and that happens much, much faster. And you, in a cluster, and happens highly in parallel, and so, yes, we do restart almost a couple of times as part of the scenario testing, but a lot of the time, for a lot of the development workflow, it's absolutely not necessary. So.
Yeah, that's a good point. On the other hand, my workflow is I'm changing the control network, and I guess maybe I can keep the nodes, or whatever.
Yeah. I mean,
changing the number of nodes and the control network. I want to try something with a 1-node cluster, 2-node cluster, 3-node cluster, 4-node cluster.
Then you do have.
And in that case, you certainly get started. But your point is well taken, right? I mean, it's like kernel modules are a good thing, and loading them, unloading them without having to reboot is a good thing, and being able to change apps is also a good thing. So, and I think, possibly your point that as an app developer, ideally the kernel just keeps running and you just unload it, and the main system just keeps running and you just keep replacing your app. So hopefully that's a little bit better. And I guess we want to think about I don't know how to document and facilitate that workflow.
And this is great, Jordan. So when you were thinking about starting on the copycat stuff, and I think that's the order that it's gonna go in, right?
Yeah.
So is that something that you would expect to be part of the order?
Yeah. So I've actually, the log. Well, so I actually wrote a prototype of this log a while back, and it's sitting in the copycat repo. Probably has tons of merge conflicts now, but I think all of it will be done in the next release.
That's cool.
And what about the other stuff?
So one of the comments we're looking at now, look at it in more detail, but it seems like one of the biggest challenges with developing distributed systems, algorithms and protocols, sort of getting them right, sort of having some kind of formal or analytical argument of why it's correct.
Yep.
And I think it only changes, what's your approach to verifying that the system, and not just the implementation, right, but actually that both, that the implementation conforms to what you think it should be, and also that what you think it should be is actually correct.
Yeah, so that's a very challenging problem. The distributed systems have modeling languages, but the problem with modeling languages is they're not code. So you can prove that you can prove that an algorithm is correct, but when you write it into code, that doesn't mean your code is correct.
Right.
So that's why I want to do this with as little changes. So there's the internal copycat protocol, as few changes as possible, because a lot of your confidence just comes from time. And I mean, there is some testing. Some of the things that I talked about in there was a testing framework for state machines, which I actually started building a few weeks ago. One of the things that difficult to know is state machines that back our primitives are responsible for basically telling copycat when operations can be removed from disk. And so I built like a proof of concept of a test framework that runs a bunch of operations against a state machine. You tell it what the log should look like under any configuration, and it just iterates through a bunch of different configurations and asserts that the log looks like what it's supposed to look like and the state machine looks like what it's supposed to look like. So that's one way. The other thing that I did in the past, there are some frameworks for testing distributed systems, like Jepsen. Jepsen is a cool fault injection. It does fault injection, and you give it a model to check. So, like for consensus, it's linearizability. So you give Jepsen a copycat client and submits a bunch of commands to the cluster, reads the outputs, kills nodes, causes partitions, and then takes all the outputs and runs them through a model checker to make sure that they adhere to your model. And there's a Jepsen repo for atomics, but it's not running right now. But yeah, my biggest thing is just trying to do something like this without changing any code. And you know, Zookeeper has this policy actually. They don't allow anybody to make aesthetic changes to code because it can change really bugs. So
it's not like the two things you just doesn't have like the state machine check around for the frame or something. But you remember, people, start seeing people present stuff on that, oh, we ran our checker against, all these route implementations, and like, all of them have bugs, right?
Yeah. Console is supposed to be one of the most stable wrapped implementations, and Kyle Kingsbury tested it with Jepsen, and it had a pretty obvious bug. I mean, that's well known in the wrap community.
Great. I think we'll probably revisit this again at the release planning. I think it sounds really good to me to take this on. But one thing I would also know that we should probably, for some of the smaller atomic things, so the mishmash ones, it would be good if you can maybe solicit the community to see if they can help some of those and provide guidance, just to spread the wealth a little bit. I mean, some of those could be done with documentation or teaching brigade, and some of those could be done, maybe with insurance or potentially even just community members at large.
Yeah, I think the goal should be to do the technical fix. I mean, I think the documentation because it's a workaround.
No disagreement there. But I mean, we should start with having the documentation, right? Because that will be useful even when we have a technical fix in place, because it can actually just be transformed into this is what the system behaves like underneath the.
Yeah, I do think exploring partition sizes makes a lot of sense, because in a 7-node cluster you have more partitions and can probably tolerate more latency on each partition.
Yep.
So yeah, I'm kind of interested in checking that out.
All right. So unless there's any other questions, then we can call it a day. Thanks, Rob. And David, are you still there?
I am there. Just had to find the right mute button.
And no, I didn't forget. I will get back with you offline regarding the process disaggregation and how this might relate, and we can revisit some other time in a TST as well. Okay.
Sounds good. Thank you.
Thanks, everybody. Bye.